Hello, everyone. We move on to study lecture 2 of module 4. In lecture 1 of module 4, we have studied the basic design method in control theory. They are applicable to the design of a robot control system. We have studied one method in time domain and 4 methods in frequency domain. Actually, the result in lecture 1 are the key takeaway from module 1. However, in order to understand the result described in lecture 1, you need to continue to study lecture 2, lecture 3, lecture 4, and lecture 5. In this way, you will be able to apply the result learned in lecture 1 to other situations in which the requirement for robot control may be different. Therefore, you need to have a solid understanding about the working principle behind the result learned in lecture 1. In addition, lecture 3, lecture 4 will also let you to be familiar with the transfer function, block diagram, and especially the condition in which we could consider robotic arm as a LTI system. Therefore, MI and O of a robotic arm will become the sum of SISO. Right? So you need to to do the study about the lecture 2, lecture 3, lecture 4, lecture 5. All right. So now we move on to study lecture 2. Before we enter the study of lecture 2, it is always good to remind you about the learning objective, which is to make you to become a designer of a robot. By now, you should be able to know that there are many generalized users in manufacturing and industry and the society. And the generalized need from these generalized users are motion provider, because they want to have a motion provider to execute motion. In this way, this machine will be able to accomplish the performance of a task, action, or jobs, etc. All right, and the motion provider should be able to execute equation of a trajectory. Then, in this sense, this is why we also call robot as a motion provider. Right? Once you know the answer to the first 2 questions, then you should be able to focus your study on the answer to question 3, question 4. All right. Then for answer to question 3, this slide shows you the generic guideline for you to come out with the blueprint of your future robot. So inside the blueprint of your future robot, you must include module 1, which is about the design of a robot software. And you must also include module 2, which is about the design of a robot's mechanism and the incorporation of actuator, sensor, controller, etc. You must also incorporate module 4, because without the control or robot control, your robot will not be able to perform programmable or reprogrammable motion. if you want to develop a digital twin or simulator or simulation of your future robot, then you need to apply or incorporate module 3, okay, into the design of your simulation software. All right. So this slide basically gives you a generic guideline for the design of the blueprint of your robot. Then in order for you to draft out the detail of this blueprint, then you need to have a solid understanding about all these topics, which have been categorized into this 4 modules. By now, you have already completed the study of module 1, module 2, module 3. Now you are doing the study of module 4. And you see the key takeaway from module 1 is for you to know the knowledge which will enable you to design robot software. All right, you can also call it as a robot's mind. All right, and the key takeaway from module 2 is the knowledge which will enable you to design the physical body of your robot. All right, and the key takeaway from module 3 is the knowledge which will enable you to design digital twin of your robot or simulator of your robot or simulation of your robot. All right. Then what will be the key takeaway from module 4? So the key takeaway from module 4 will be the knowledge which will enable you to design your robot's control system. Because when you want to sell your robot as a product, your robot must fulfill this requirement of being motion provider. And the motion to be performed by your robot must be programmable and reprogrammable. All right. So now we continue with the study of lecture 2. So in lecture 2, we are going to look into the detail of dynamics under control. So you remember in lecture 1 of module 4, we actually have exposed you to many concepts in control theory. One is about transfer function. One is about the block diagram. One is about the negative feedback control. All right. And inside the negative feedback control diagram, you see there are 3 basic building blocks. Number 1 is the dynamics of a system under control. Second one is the sensory feedback. And the third basic building block is the controller. So you see inside the feedback control loop, there are 3 basic building blocks. One of them is dynamics under control. Okay, so the key takeaway from lecture 2 is for you to understand what will be the dynamic equation of a robot under control. All right. Then from the study of module 2, you understand in general, a robotic joint consists of a combination of power joint, torque joint, and the link joint. Therefore, we need to know the dynamic equation at the link joint, dynamic equation at the torque joint, dynamic equation at the power joint. This is because robot's brain can only issue signal. Then this signal will control the release of energy from power joint. Therefore, we need to know, how will be the control signal, is related, be related to the motion to be performed by robot base or robotic arm, etc. All right. So then we just go into the detail at each level about the dynamic equation. Okay, so we start with dynamic equation at the link joint. All right. What do we mean by dynamics? So by definition in robotics, Okay, I believe in module 3, you have studied the definition of dynamics and kinematics. And in module 2, we have also given you the definition about the kinematics and the dynamics. Okay, so in robotics, dynamics means the relationship between motion and the energy. Okay, so therefore, we need to know the source of energy inside your robot. Okay, for example, in this diagram, then we know that the source of energy comes from power amplifier. Behind the power amplifier, we must have a power supply system. It could be a battery or other power source. Okay, then through this device, the electric energy will flow out. And in physics, every one of you knows electric power is equal to what? Is equal to voltage times current. Okay, so you see input to actuator motor will be electric power. Then in mechanic domain, mechanic power is equal to force times velocity or torque times angular velocity. So tau times omega equal to or represent mechanic power. Therefore, the input energy comes from electric domain, then output energy will be manifest in mechanic domain. Here you must always remember there's energy conservation. We can never destroy energy. We can never create energy. We can only transform energy from one domain to another domain, from one place to another place. All right. So there's an energy conservation principle for us to understand, to follow. All right. So this just for you to know, okay, what do we mean by dynamics in robotics? So basically we want to know relationship between energy and the motion, all right? Since a robotic joint, okay, here is highlighted by this, this diagram, okay? The robotic joint consists of a combination between or among the link joint, torque joint, and the power joint, okay? Therefore, we have this relationship at the input of a link joint, input of a torque joint, and also input to the power joint. Therefore, there will be 3 relationships. Okay, so we start to look at the relationship at the link joint first. All right, and before we look at some example of dynamics at the link joint, it is always good to remind you about the background knowledge, which is the use of Newton's second law. In order to use Newton's second law, we need to know what is the net force acting on a rigid body. Okay, then once we know the net force acting on a rigid body, then we know the acceleration produced by the rigid body due to the net force. All right. Then what is acceleration? Acceleration means the first order derivatives of a velocity. Then what is velocity? Velocity means the first order derivatives of a position. Okay, so I hope you will be clear about this background knowledge. Okay, then how to determine net force? So net force is equal to the sum among acting force, external force, and gravitational force, gravity. Okay. Then you may ask this question, how to determine external force, okay? So in mechanic domain, external force may be due to gravity, external force may be due to interaction, external force may be due to risk of friction, external force may be due to angular motion, because angular motion will induce a centrifugal force, for example, okay? And external force may be due to radial motion. Typical example is a Coriolis force, okay? So when you undergo a linear motion on the rotating platform, then there is a Coriolis force being induced, all right? So I will just show you, okay, some example about the nature of this force, okay? And then here you see we have a keyword, interaction, because this gravity due to the Earth, Then this is due to the motion. When there's a friction or something like that, then this could be due to the self-motion. This could be due to the self-motion, etc. How about this one? Interaction with the people, with the environment. Therefore, we need to know how to determine interaction force. Okay, so I just show you this example. Okay, for example, you have a robotic arm to mount the wheel onto the body of the car. Then in this case, between the hand of this robotic arm and the workpiece, in this case is the body of the car, there must be an interaction force. Okay, so in module 3, you have a study robot statics. Okay, so here I just show you the static equation. So it means in order to produce this interaction force, we need to apply this extra torque at each joint inside the robotic arm. Then how to determine this extra torque for interaction? The solution is transpose of Jacobian matrix times F. Now you may ask this question, what is this Jacobian matrix? Jacobian matrix comes from motion kinematics. Then what is motion kinematics? Motion kinematics is an equation which relate the velocity in joint space to the velocity in path space, or to the velocity of the two tips in path space. Okay, so the subsequent slide I will show you a little bit detail, so you can treat this part of a lecture as a kind of a revision about what you have studied in module 3. Okay, for example, for a robotic arm, we can put all the torque and all the motor or link joint together to form this torque vector. Okay, assume we have n joint, then we put the tau 1, tau 2, tau n together to form this vector. Then for each joint, we may have an angular position or linear position. Then we lump them together, call them as a generalized coordinate. Okay, if you have an n joint, then we have an n generalized coordinate, q1, q2, qn. Okay, q1 may refer to angular position or linear position. Okay, so we just lump them together and call it as a generalized coordinate. All right. Then this equation shows you the motion kinematics. Okay, because for the two tips, we assign a coordinate system to it. Okay, then for this coordinate system, we can talk about the linear velocity of the origin of the coordinate system assigned to the two, plus angular velocity of the coordinate system assigned to the two. Okay, this angular velocity actually is equal to equivalent axis of rotation times equivalent angle of rotation. Okay, so it's equal to the translate of equivalent of angular position about the equivalent axis of rotation. Therefore, this is a vector with the 3 elements. All right, so we put them together, then we have a vector of 6 elements. Then this vector is related to the angular velocity of a generalized coordinate, okay, inside the robotic arm. Okay, then this time the Jacobian matrix. Okay, so then you will obtain this equality. So this is the meaning of a Jacobian matrix. Then we use this one to determine additional torque or additional energy in order to support this interaction with the environment. Okay, the transpose of Jacobian times required interaction force, then allow you to calculate what should be the additional energy released by the motor in order to contribute to the interaction. All right, so this one will be the intended force for robot to act on the environment. Then we may have an unwanted force, for example, due to visco friction, because when we start to move, ideally we do not want to see this friction to appear, but in practice, this friction force must be there, so we cannot ignore them. But this force is unwanted, it's not intended. We do not want to see it, but however, we must consider it. All right, so I use this example. to illustrate. So you see, when there's a motion, then there is a resistance to the motion, and this resistance is proportional to velocity. Okay, so then you have this coefficient times okay, the velocity. So this could be kinetic friction, or for rotary motion we call it as a visco friction. All right, so this is a nature of a visco friction. Then how's about the unintended force due to rotational motion, for example, centrifugal force? All right, so therefore, when you have an object, let's say when you have a rigid body move along the circular path, for example, in this link, let's say link 2 will drive this vertical link. When link 2 undergo rotation in the horizontal plane, then this rigid body will move along the circular path channel. It's like this is the mass of this vertical link, and this is the length of the second link of this scalar robot. When this move, then you will see a centrifugal force, which will move away from the axis of rotation of a second joint. All right. So then what will be this centrifugal force? So this centrifugal force is equal to the mass times centrifugal acceleration. Centrifugal acceleration is equal to circular velocity squared divided by r. Then what is circular velocity? Circular velocity equal to angular velocity times radian. Okay. Then you can cancel the r. Then you have a m mass times okay, radian times omega means is angular velocity, so that is equal to the first order derivatives of angular position. All right, then you have a square. So this gives you the formula for you to determine this external force due to or induced by angular motion. All right, and again, this is unbounded, but it will be present. Okay, once you start to move your robotic arm. All right. And this is another external force induced due to radial motion on the rotation platform. Okay, for example, this link undergo rotation. Then we have another object move linearly along this link. Then in this case, you will see another external force, which is called as a Coriolis force. Okay, but of course, when this rotate, you have a centrifugal force in the radial direction, but Coriolis force is perpendicular, okay, to V. So you see, this is not the centrifugal force, okay. So this is a Coriolis force. This force has been discovered by this French engineer called Coriolis. This is why we use his name to name this force. All right, okay. Then mathematically, this force is proportional to this angular velocity, proportional to the linear velocity, proportional to 2 times the mass. All right, so this is a formula for us to calculate this force in this direction. So which is perpendicular to V, perpendicular to omega vector. All right. Okay. Now we just use this simple example for you to do a little bit of practice for you to know. Okay, what will be the relationship between the net force? Net force means overcome all the external force, and then the remaining energy will contribute to the acceleration of the mass. Okay, so we just consider the last link, which is a vertical link with the mass m. Okay, so we have an acting force, then there is a visco friction when it moves. Okay, so the first step of the solution is to do a quick analysis about the question in order to derive the key information from the question. So we know the last link has a mass m, and the external force acting on the last link is F. And we use Q to represent the generalized coordinate. But however, in this case, it's a linear motion. All right. And the visco friction coefficient is denoted by K. Then second step is draw free body diagram. Okay, so for any mechanics system, in order to derive a dynamic equation, this is a common practice. Regardless the complexity of a mechanics system, we always treat as a set of rigid body. Then for each rigid body, we draw the free body diagram. Then we apply Newton's second law. Okay. So in this case, we just identify all the forces which will contribute to vertical motion. Okay. So we have an acting force, we have a frictional force, we have a gravitational force pointing downward. Okay. Then the net force will be the sum of all the external force acting in the direction of the motion. So in this case, we only have 3. So apply the force minus visco-frictional force minus gravitational force. Then we apply Newton's second law. This net force will produce acceleration by the mass m. All right, acceleration is equal to double dot of the position. Okay, then we shift these 2 terms to the right-hand side. Then we swap the equality. Then we get this equation. And later on, you will see we can extend this equation to the case with a magnetic system of n rigid body, because this is for 1 rigid body. Okay, if we have n rigid body, then you will see the equation is quite similar to this one. Okay, instead of using scalar, then we have a matrix. That's it. All right. So this will help you to understand the general equation of dynamics with n rigid body inside robotic arm. All right. Okay. Then I show you one more example. This is to help you to understand the equation of statics. Here, we just simply apply, okay, this equation of statics. Okay, in order for you to believe in this equation or understand this equation, then okay, from the result of this example, then immediately you understand the physical meaning. For example, we just supply enough energy for this robot to maintain the 2 links at this position at the rest. Okay, so stand still. But stand still, that means we just apply energy which is enough to overcome the gravitational force. You see, you have a M1G acting on link 1, M2G acting on link 2. Okay, therefore, we need to overcome these 2 external forces. Okay, then what should be the desired power 1, power 2, like this. Okay, so we start with link 2, because for link 2, then you see what will be the external force which will produce a torque at the joint 2. Then in this case, because link 2 is supported by link 1, so link the joint 2 will only be used to control link 2. So therefore, is M2G will produce a torque which will act at the joint 2. Okay, M1G has no influence on joint 2. All right. So then in this case, in order to maintain this angular position of link 2, assume the angular position of link 1 is 0. And later on you will see orientation of link 2 or angular position of link 2 depends on angular position of link 1. Therefore, based on this observation, immediately you understand robotic arm actually is not LTI system. It's because even, let's say we study this relationship depends on theta 1. Okay, even we don't change theta 2. So it means what? Today, theta 1 could be equal to 0 degree. Tomorrow, theta 1 may be 20 degree. Then the relationship changed, Jonah. Okay, so it's not time invariant in this sense. All right. So strictly speaking, robotic arm is not LTI system. All right. So let this example help you to understand. So then in this case, M1G, then what is the moment arm of M1G? Moment arm of M2G is equal to L2, half of the L2, the link length of L2 times cosine theta 2. Okay, so half of the length of link 2 times cosine theta 2 times M2G should be equal to the torque, external torque, okay, due to M1, M2G. Then the motor here must produce additional torque, tau 2, which is exactly equal to the external torque due to M2G. Once we have this equality, then they cancel out, then there's no additional energy, then there's no angular acceleration because the net torque equal to 0. Tau 2 minus this one equal to 0. Okay, all right. Then when theta 1 has a value is not equal to 0, then you will see angular position of link 2 become a theta 1 plus theta 2. Therefore, the moment arm of M2G become cosine theta 2 plus theta 1. Okay, and here you can always imagine this one also depends on M1G, but however you time this as a 0. This is just for mathematical convenience. Therefore, then this equality could be written in the form of multiplication between vector 0 and this one times this vector, because I can put the M1G and M2G together to form this force vector. So this shows you that the interaction with the external force is a multiplication between two vectors. Okay, so because you see there's a static equation is equal to tau equal to J transpose times F. Okay, so now you see J basically is something looks like 0, and this one with these two elements. Okay, F is like M1G and M2G. So you see, so this, okay, this is for you to understand the equation of statics, right? Then for the torque at the joint 1, then you will see M1G will produce external torque at the joint 1. M2G will also produce external torque at the joint 1. Then the motor at the joint 1, tau 1 must produce the torque which is equal to the sum of these two external torque. Okay, the moment arm of M1G is equal to half of link length of link 1. Okay, so the L1 times divided by 2. And the moment arm for M2G should be equal to L1 plus half of L2 times cosine theta 2. This is for the case when theta 1 equal to 0. Then what happens if theta 1 is not equal to 0? Then orientation of link 2 is equal to theta 1 plus theta 2. Therefore, the moment arm of M2G will be equal to link 1 times cosine theta 1, half of link 2 times cosine theta 1 plus theta 2. All right, so you have this moment arm. Then for the torque due to M1G, moment arm of M1G, then it should be equal to the half of a link L1 times cosine theta 1. Okay, so again, so if let's say we put this one together to form this interaction force vector, then you will see you have this one plus this one. Okay, you can put them into another vector. That vector looks like a Jacobian matrix, something like that. All right, okay, so then we put this together, then we have this relationship. So you will see the torque to be provided at the joint 1, joint 2, okay, is a function of theta 1, theta 2. So in other words, if let's say we supply tau 1, tau 2, okay, if they are big enough to overcome this value, then you will see theta 1, theta 2 will have acceleration, right? So this is for you to understand the relationship, okay, between energy and the motion. All right. So, and if we want to, okay, use this equation to calculate the desired torque at the joint 1, desired torque at the joint 2, therefore we can, okay, construct this feedback control loop, because this is calculated by the equation of statics. Okay. So as long as the actual tau 1, tau 2 equal to the desired one, then this robot arm will stay at this configuration and the rest. All right. So then we just use a closed loop control system to achieve this result. All right. Okay. Then I show you one more situation. Then what happens if, let's say, the two tips of this robot arm has interaction force also with the environment. For example, this arm carry a screwdriver. The screwdriver will exert force F on the ceiling. Once this one apply force on the ceiling, then ceiling will have a reaction force acting on the two tips of the robot arm. All right. So then in this case, we have an extra component. Okay. So it's like in example in the result in the previous example. So we just add in this extra torque due to this reacting force. So this reacting force will have a moment arm, which is equal to L1 plus L2 times cosine theta 2. For joint 2, then the moment arm of F is equal to L2 times cosine theta 2. Okay, so then this is extra torque, okay, which must be produced by joint 2. All right. And when theta 1 is not equal to 0, then moment arm of F will become L2 times cosine theta 1 plus theta 2. Okay, so just modify it. Then again, we can put this 0, look, the M1G, M2G, F together. So this is a interaction force with the environment. But for this one, we take gravitational force into account. We treat gravitational force as an external force. All right. Okay. So then you will see tau 2 is equal to this vector times another vector with this element 0, this one, and this one. So then you see it's more or less looks like a static equation, which is equal to J transpose times F. All right. Okay. Then for the torque at the joint 1, then you will see this one will produce a torque which is equal to force times moment arm. Moment arm is equal to L1 plus L2 times cosine theta 2. You see, okay? So you have an additional term here. If theta 1 is not equal to 0, then the moment arm will become L1 times cosine theta 1 plus L2 times cosine theta 1 plus theta 2. Okay, so then this moment arm will change, become this expression. So again, you see we can put the M1G, M2G, F together to form this interaction vector. All right, then you see the relationship for robot statics, so which is equal to J transpose times F. That's it. All right. Okay. So then we can have this open loop control system. So it means if let's say we let the motor 1, motor 2 to produce tau 1, tau 2 with these two desired value, eventually this robot arm will stay at the rest in this configuration. But however, in practice, if you have a slight disturbances or error in the modeling, okay, of the system, or if you have a slight variation in the dynamic parameter or kinematic parameter or geometric parameter of the robotic arm, then this open loop control scheme may not work. Okay, so it's not precise. So it's always good to use this magic result in control theory, which consists of constructing this negative feedback loop. Okay, then in this case, you can overcome the variation disturbances, because the job or the mission of the controller is to make this error to be 0. Okay, regardless variation or change inside the system. All right. So then from here, then you see the way how to design a control system. All right. So then how's about the situation in general? Let's say we have a robotic arm which has a 6 degrees of freedom. Then the answer will be like this. Okay, because each joint will output the torque. When we put all the torque together, then we have a torque vector. then this top vector will overcome the energy spent on interaction, overcome the external force induced by the radial motion or external effect due to gravitational force. Then the net energy will contribute to the acceleration, okay, by this moment of inertia, okay. So this is correspond to the mass. If it's a linear motion, then it's a mass. If it's a rotary motion, then this is a matrix of a moment of inertia. All right. Then we shift all these three terms to the these two terms to the left-hand side. Then we have this standard dynamic equation for a robotic arm with n degree of freedom or n joint inside. Okay. So that means the top come from each joint. Okay, we put them together into a vector, minus out the energy spent, okay, for interaction with the environment. And remaining energy will be used to overcome gravitational effect, overcome Coriolis force. Then remaining energy will contribute to angular acceleration by this moment of inertia. All right. So this is physical meaning. Okay. So this is an equation. Okay, dynamic equation at the link joint. All right, done already. So now we know this. Then we must move one step further. We need to know dynamic equation at the top joint, because the energy at the link joint come from top joint. So the first relationship tell you the relationship between motion and the energy at the input of link joint. Then how's about the relationship between energy and the motion at the input of a top joint? Okay, so we must move one step further. Okay, so then we need to know, okay, what will be the relationship between input top to the top joint and the output the top from the top joint. The answer will be tau is equal to k times tau m. Okay, so then if let's say we have n such a joint, then we can have this relationship for each of them. Okay, so we just use I to indicate this is I's joint. I equal to 1, 2, 3, 4, or n, something like that. All right. So then we can put the input top to the link joint together to form this vector, and the angular position of link joint together. This is generalized coordinate or generalized position, angular generalize the position of link joint. Okay, so you have Q1, Q2, because this position may refer to linear position or angular position. All right, and similarly, we can put all the top to the input of top joint together to form this vector. Okay, tau m1, tau m2, tau mn, and also the generalized position at the input of top joint together. Then we have a qm1, qm2, qmn. Okay, since the relationship between output from the top joint and the input to the top joint, okay, described by this one, then you see top joint basically amplifies the top by factor of a k. K is also called as a speed reduction ratio. Okay, so then we have a system of n such an equality because I vary from 1 to n. Then we can write this system of equation into this matrix form. The inside KR is a diagonal matrix. Okay, then we can also compute the inverse of a KR. Then we have this relationship. Okay, this is a relationship which tell you that the tau is a function of a tau m. Then this relationship tell you that the tau m is a function of a tau. Okay, so then you have a property one of a top. Then how about the angular coordinate position? Because we can also put the position at the input of a top joint together to form this QM matrix. Okay, then position at the output of the top joint together to form this Q matrix. Okay, then individually, then we know, okay, position at the output of top joint is equal to position at the input of the torque joint divided by speed reduction ratio. Then we have n such an equation. We can lump all these equations together to have this matrix equation. Okay. Then here Kr again is a speed reduction ratio matrix. All right. Then if we compute inverse of this one, then we have this relationship. And this Qm is a function of Q, or Q is a function of a Qm. All right. Then next, we try to split this inertia matrix of moment of inertia into two terms or two components. First component is a diagonal matrix with all the diagonal terms. Second matrix is off-diagonal matrix. For example, for any matrix, you can always imagine it to be the sum of these two matrices. First one is a diagonal matrix. Second one is an off-diagonal matrix. Okay, so any matrix can be written in this form. Okay, so this is just for simplicity. Then for corollary matrix, we just use a C to represent it. With this notation, then we are ready to convert dynamic equation at the link joint to dynamic equation at the torque joint. Okay, so we substitute Q by inverse of a KR matrix times QM. Substitute this one by C. Substitute this one by B diagonal matrix and the off diagonal matrix. Then substitute this one by matrix KR times tau M. Okay, then we have this equation. All right. So this is a dynamic equation at the torque joint. Okay. Now we ask you to prove this expression. So tau M is equal to a matrix times QM double dot plus extra term. Extra term equal to the sum of these three terms. So this looks like a matrix form of Newton's second law. Okay, Newton's first law is what? The net torque contribute to the angular acceleration by a moment of inertia. Okay, so then you see the physical meaning is the same. Okay, the net torque, the torque minus this one, the net torque will contribute to the acceleration of a generalized coordinate. All right, so this is the physical meaning. Then we want you to use this to prove this result. Okay, it just prepare you to understand the meaning, basically to understand the meaning of this equation. Okay, if you write in this form, then you have a better understanding about the meaning of this equation. Okay, so first step, we separate this term into sum of two, because this is a single term with a QM double dot. Now we have a two term with a QM double dot. Okay, because we want to focus on this one, because this matrix is a diagonal one. Okay, so it's very meaningful. Later on you will see, okay, why to have a diagonal matrix. I guess in tutorial 4 you will see, okay, the usefulness of having this expression. Okay, then you have another second term with the QM double dot, the rest remain the same. Then next is to swap the equality. Okay, so equality here, then we swap. Now this become a left-hand side, this become right-hand side. After that, then both sides times the inverse of a KR matrix. Both sides times inverse, then left-hand side become tau M. Then right-hand side, you have this. Then you see, you have this one already, okay? Then we lump all this together to name them as D, okay? So lump these three terms together and name the result as a D, then you have this expression, okay? So this looks like Newton's second law in the case of a matrix equation, all right? Okay. So then from this equation, we want you to prove this one. So this is just for you to know that the acceleration is proportional to input energy. So this is this meaning, so if you have an input, which is a tau, then output will be acceleration. Okay, so this is for you to later on to draw the flow of the signal in frequency domain. Okay, so then from this Newton's second law in matrix form, then we shift this to the left-hand side, then swap the equality. Then left hand side become a right hand side. Then we have this. Now both sides times inverse of this composite matrix. Okay. Then we will have this result. Okay. So here you see we compute the inverse of this composite matrix. Then we apply this rule. If let's say we have an ABC times together, if we want to compute the inverse, the result will be the multiplication of an individual inverse of this matrix, but in reverse order. Because here you see A come first, followed by B, then followed by C. Now C come first, followed by B, followed by A. So you reverse the order, then you compute individual inverse. So you apply this rule to this case. Then you will see inverse is equal to itself. Then this one become inverse. All right. So you get this result already done. Okay. Then we move one step further. Okay, at the power joint, because energy actually come from electric motor or power joint. Therefore, we want to know, okay, at this level, what will be the relationship between motion and the input energy, right? Okay, so this slide basically show you mechanical energy at the output of a power joint come from the electric energy at the input. So this is a power joint. Output is mechanical energy, input is electric energy. From here you see you have electric power in the form of V times I, then you have a mechanical power in the form of tau times omega. All right, so then we want to know, then what is a power joint? So actually power joint is an electromagnetic device, okay, which convert electric energy into mechanic energy, okay. Then the equivalent diagram for electric motor is shown by this slide. So you will see for the power joint has a mechanic property plus electronic property. Mechanic property is just a rotating payload. That means you have a shaft which will drive a payload. This payload could be anything. The payload could be the subsequent link 1, link 2, or link I plus 1, link I plus 2. Okay, so you can lump it to make it to become an equivalent moment of inertia. It's just a payload. Okay, then is a rotation shaft. Then rotating shaft will supply torque. Okay, mechanical energy. Then at the electronic side, a motor basically is a RL circuit plus okay, this electricity generation device, because you have a coin which rotate inside the magnetic field. When a coin rotate inside magnetic field, which will produce voltage. Okay, so then this behave like an electricity generator. Okay, so this is the equivalent circuit. Then apply the voltage will produce a current which will flow through this circuit. So apply the voltage minus out the voltage produced by this electricity generation effect. Then the net voltage will produce a current across resistor and the inductor. All right. Then we can write down this equation now. Okay, the voltage drop at the input from the electronic side should be equal to the voltage drop across resistor plus voltage drop across inductor plus voltage produced by rotating coin. All right. So voltage produced by rotating coin is proportional to angular velocity of a rotating coin. Okay. Then voltage drop across inductor is proportional to first order derivatives of the current. Then voltage drop across resistor is proportional to current. So therefore, we have this equation. Okay. Then in general, we have this relationship which relate electric energy to mechanical energy. Okay. So we can assume that this relationship is a linear relationship. In other words, mechanical energy at the output is proportional to electrical energy at the input. Okay, so here we call it as a motor constant. Okay, All right. Then from this one, then we know what is a relationship between I and the tau, and what is the relationship between first derivatives of I and the first derivatives of the tau. So you will see this is the input to the motor, then this is the output from the motor. Okay, so we call this one as a dynamic equation 1. All right. So, and we can first find out the dynamic equation 2, which show us the relationship between mechanical energy and another parameter which represent electric energy, and this one is a voltage. Okay, because I is just one parameter which indicates the electric energy, because we have another one, V. Okay, then how's about relationship between voltage and mechanical energy, tau? Okay, represented by tau. Okay, right. So then we continue, because we from this property at the electronic side from electric motor, we have this dynamic equation. Now we substitute I with this relationship, substitute first order derivative of I with this relationship. Then we get this equation. Okay, so you see voltage is a function of tau, and Q and dot. All right, so we can call this as a second dynamic equation of a power drum. All right. Now we look at the dynamic equation under control, because this energy come from somewhere, come from a controllable device, which is controllable by robot brain. Okay, so because we may ask this question: how to control the release of this electric energy? Okay, if this energy is not controllable, then there's no use. Then your robot is not controllable. Okay, understand? So we need to make electrical energy to be controllable. Then how to achieve this goal? Solution is what? To have a power amplifier. Then power amplifier could be controlled on the signal from robot's brain. Robot's brain is called as a controller. All right. So then we need to know what is the relationship between this signal and this voltage, or this signal to this energy here. Okay, because this one is controllable by our brain, by our program. Then immediately you know, okay, through the software, robot software can control this one. Then this one can control this one. Then this one can control this one. Then your software can control the motion of your robot arm. Okay, so this gives you this understanding about the flow of the signal and the flow of the energy. All right. Then what should be the equation or dynamics for power amplifier? So actually there are many type of power amplifier. Then I just choose this example to help you to understand the relationship between signal and the electric energy, because this represents electric energy. This signal represents actually the knowledge. For example, I want to perform this task, I want to perform this motion, and all this knowledge could be decomposed into the value of a motion parameter. So this may correspond to the motion parameter. So this is a signal which represents knowledge. This is a signal which represents energy. Okay. Then what is the relationship? If we follow this diagram, then you see, I guess it's quite easier for you to work out this solution. Okay, from the bottom branch, so you see this voltage V2 divided by R1 plus RF equal to the current. Then this current times RF will give you the VF. Then VF is equal to this VF. Then V1 minus VF give you the current. Then this current times RF give you this voltage drop. Okay. Then VF minus this voltage drop give you the V output. Then you simplify it, you should be able to get this very simple relationship. So you'll see the output voltage is proportional to the difference of these two input voltage. Then we treat V2 minus V1 as a control signal to the amplifier. Then you see So this is we treat it as a static device. So this is a typical example of a static system. Okay, there's no transient response. All right. Now we can put them together. Okay, substitute this one by this equation. Okay, because VAI equal to VCI. C means controller. Okay, then we obtain this dynamic equation, which relate control signal to mechanical energy. All right, so this is the dynamics under control of your robot. All right. Okay, then this slide basically summarizes the signal flow and the energy flow. So you see, start from a signal, which is the output from your brain, from robot's brain. Then this will control release of electric energy. Then release of electric energy will control will affect the amount of mechanical energy. Then this amount of mechanical energy will produce this amount of motion. All right. So then, okay, this slide help you to understand the signal flow, energy flow. Okay. So this is a signal. So, and these are signal behind them, they are energy, because this is a signal associated with energy. This is a signal associated with energy. This is a signal associated with energy. Okay, so you see behind this signal flow, there is energy flow. All right. So that's all for lecture 2. So the key takeaway from lecture 2 is for you to understand, okay, the dynamic equation under control for your robot, because inside the closed loop control system, there are 3 basic building blocks. First one is the dynamics under control. Second one is a sensory feedback, and the third one is a controller. Okay, so in lecture 1, you understand the principle or methodology for you to design the controller. In module 2, you have studied one or a few examples about the working principle of a sensor. So by now, you understand, okay, the full dynamics of a robot, because in module 3, you have a study dynamics at the link joint. Okay, now with lecture 2 of module 4, now you have a full picture about the dynamics of a robot under control. All right, so that's all for lecture 2, and I'm looking forward to seeing you in the study of lecture 3.